Okay. So, we considered complex random variables and then complex covariance matrices and the Hermitian matrices, their properties, and a special kind of Hermitian matrix called positive definite matrix, where the eigenvalues are not only real, they are positive and it is always invertible. Then we showed that it is reasonable to assume that correlation or covariance matrices in most cases are actually just not Hermitian, they are also positive definite, that we explained in detail. Now, I will go to a topic which I think you may be aware of, and that is called random process, discrete time random process. That is discrete time random process. Suppose, as before, I am carrying out an experiment and recording the observation, but experiment is like this. Every time I conduct an experiment, a waveform results. A waveform can be continuous analog, I can sample it, so it will be a discrete time one, or it can be discrete time itself. Like suppose I say IIT and I record the waveform in a serial and then sample it. So, I get a block of samples, there is a sequence. Next time I say the same, make the same experiment, say IIT, you are sure you will not see the same waveform. Okay, it is random, you will see different waveform and so on and so forth. But interesting thing is, any of the waveform if you play into a loudspeaker, it will produce the same sound IIT, the waveforms are different. Isn't it very interesting? This is because these waveforms, they all belong to one particular class of random process, one random phenomenon, which is associated with the word IIT. So, every time I make the sound IIT, I get different waveforms, but they all belong to the same category. So, this phenomenon of generating this random waveforms, okay, they basically they are described as, they are basically termed as random process. Like if I say x of n is a random process, means x of n every time I observe there will be a discrete, I am talking of sequences. So, x of n is a sequence, every time I make an observation there will be one sequence x n. Every such observed sequence is called a sample function, okay, and sample functions vary from experiment to experiment. So, x n as such is a random process and any observation of it will be a sequence which is called a particular sample function, sample observation, sample function. X n as a whole will be called a random phenomenon and it is more popularly called as random process. I would rather love to call it random phenomenon. So, x of n is a random phenomenon, like speaking the word IIT, and whenever I measure it, observe it, I see a waveform, discrete time waveform, which is a particular sample function. And if I collect all possible sample functions, in this case there will be infinite such sample functions, then that collection, this entire set is called ensemble. So, one is sample function and collection of all possible sample functions called an ensemble. All right. Sequence like this. It is just a sample function. It can be finite in duration, can be infinite in duration, does not matter. Next time I observe, I will take another, I will find another discrete time waveform, another sample function, and so on and so forth. But each such sequence, when played into a loudspeaker in that experiment, in that example, will produce the same word, okay, same sound, IIT. So, they all belong to one particular class of random phenomenon or random process. Okay. Now, here every sample is a random variable, because if you consider this to be nth index, this point, next time when I observe another sample function, I am sure you will not see the same value, its value will change. It can be complex or real, but its value will change, because every sample at every point is a random variable, it is random, randomly fluctuating. Okay. So, that means every sample itself is a random variable, because if I make another observation of x n next time, I will say totally different waveform. So, at nth point I will see another value of the sample, okay, not this. That means, if I restrict myself to a particular index n, nth point, remain there and keep observing the sample value, I mean as I go on doing the experiment, there is observe various sample functions one after another, I will see different values, scalar values for this sample. So, this sample will be sample that is located at nth point will itself be a random variable, right. Okay. Now, suppose I take the random variable x n, this is my x n, suppose here it is a particular sample, here there is a difference between these two x n, this is the entire class random process and this is a particular waveform, particular sample. Okay, those same notations are used. When I say E of x n, nth sample, it is a random variable, I take its expected value. So, expected value will be mu. In general, it will depend on where this sample is located, because I may not get the same mean at n plus 1 or at n minus 1 or n minus 2. That is why I should put an index n, all right. And there is another thing, correlation. Suppose x n, and I am talking of complex case to be more general. So, in the case of complex case, if one random variable is x, another is y, then we take x y star as the correlation, right. So, x is x n here or y may be another sample k point away, okay, from nth point, maybe here n minus k. If k is positive, it could be right hand side also, if k is negative, okay. And this product x into y star expected value, there is a correlation. Correlation also should in general depend on what are the locations of these two samples, because I can pick up any other two samples, take their correlation, that will not be in general same as this. So, it will be dependent on or x x, if I call x x, it will be a function of both n and n minus k, this point in general. There is a class of random process called wide sense stationary, WSS, random process. Here first we assume mu n does not depend on n, it is fixed at all point. It means the waveforms are fluctuating one after another as I do experiment after experiment or experiment, but the randomness, the fluctuating property randomness, okay, is not having any bias on a particular zone of this axis. I will see the same degree of randomness at say this point, nth point, to same degree of fluctuation or randomness at n minus 1th point, and so and so. And therefore, the mean of this random variable here at nth point or this random variable here at n minus kth point, that all that will be same, because there is no bias on a particular time point or on a particular zone in this axis. You will find it is under the assumption that the randomness, the property, this is a fluctuation, fluctuating nature, randomly fluctuating nature. This is uniformly distributed all over this axis. You will find the same behavior at nth point, same behavior of fluctuation, random fluctuation as at this point, as at this point. Therefore, the mean, if we make this assumption, of course, this is an assumption we make. Okay. Therefore, mean should not depend on whether I am at nth point or n minus kth point or 0th point or minus 1th point. So, it should become independent of n, independent of. Often we take zero mean random processes, meaning mu n 0 for all n. See, mu n is 0 for all n, that means again mu n is independent of n, because you may, whatever n you choose, whatever point you choose, the mean is same. So, that becomes a special case of this. So, often actually in practice we take 0 mean random processes which satisfy, of course, qualify for this, all right. And making 0 mean is not a problem if it is really satisfying this kind of thing, that mean is same at all points of time, then it is just a question of subtracting mean from every sample. So, it becomes 0 mean, every sample is 0 mean. So, it is not a big deal. So, this should be, for this assumption to hold White-Stein stationary random process, mean should be independent of n, mean of any point of time should be independent of n. And secondly, correlation. Correlation should depend on only how close or how far these two samples are. Okay, that is the gap. If they are in general, if they are close by, correlation is naturally expected to be higher. If they are far away, correlation is supposed to be less. So, it should depend on just the gap. So, whether I take these two samples or whether I take two samples here, if the gap is k, like gap is k here, between these two samples or between these two samples, correlation should not change, because correlation should depend only on the gap, not on the absolute locations. Because again the correlation property is not localized on this axis. Okay. It is uniformly given, uniformly distributed over this axis. So, correlation between two samples at k point apart, whether I see them here or elsewhere, like between them, I should see the same thing. It is the gap that should matter, not on the absolute locations. Okay. That means, in this case n minus k should depend only on k, all right, only on k. So, if these two assumptions are satisfied, or we make these two assumptions, then it is called White-Stein stationary WSS random process. So, correlation depends only on the gap between the two sampling points, not on the absolute values, absolute locations, and mean is independent of the sampling point chosen n. Okay, it is same for all indices. All right. One thing, so I come to the next page. So, now then I rewrite R x x k is nothing but, as we have seen, E of x n x star n minus k. It depends only on the gap. So, one thing is, what is R x x 0? R x x 0 is E of x n x star n minus 0, that is x star n. So, x n x star n, okay. So, of course, mod x n makes it real, square makes it, and mod itself makes it non-negative, it cannot be negative, square, okay, expected value. So, it is a power, total expected power. Okay. Total sample is taken, its mod value squared. I am not subtracting mean here, but if the mean is 0, then it is also x n also is the increment around the mean. So, it is the incremental power expected, which is the variance. So, for 0 is the total expected power for the nth sample, okay. And this should not be under WSS assumption, this should not depend on n. So, it is just for any sample total, first this is power, total power, because I am taking the whole of x n, I am not subtracting mean from it. So, mod of that square, total power expected value, that is R x x 0, and obviously that is greater than equal to 0. Usually it is greater than 0, but equal to 0 means expected value of mod x n square 0 means in all trials x n takes 0 value, then only if x n is 0, then only mod of x n is 0, mod square is 0, and if in all trial it takes 0 value, then only expected value of that mod x n square can be 0. which means xn is a 0 random variable. Its value is always fixed to be 0 in all experiments. That normally does not happen in our cases, okay, and that is why it is usually greater than 0. Anyway, this is one property of this is called autocorrelation function. This is called auto and another thing, what is Rxx minus k? It is E of xn x star n minus k. Then what is Rxx conjugate minus k? So, you have to take conjugate this entire thing here, conjugate outside, but and this is a complex number, right. Xn is complex, this complex number. If you call it z, so E of z star we have seen earlier is E of z star. So, it is nothing but E of, if you call this product as z, E of star of that, and star of that is means star on this, star on this. So, x star n I write on this side and star cancel. So, x n minus n, sorry, this is plus k, n minus k. So, it was minus, k is minus k. So, if it is minus k, it becomes plus k. All right. If n plus k is a point, you call it m. So, this is n is n plus k is m, n plus k is m. So, this is m minus k. So, it is E of x of m x star m minus k. So, again because it is WSS, it does not depend on the absolute location m and m minus k, it only depends on the gap between the 2 points. The one without star take the point to be m, the one with a star take the point to be say m minus k, and then subtract this from this, that is the gap. So, m minus bracket m minus k, which is k. So, again it is nothing but the autocorrelation at k. So, I write this way Rxx k, this I write on the left hand side is same as Rxx star minus k. This is called the Hermitian property. Of the autocorrelation function. What is the consequence? Suppose given xn to be White's stationary random process. Let xn be a vector consisting of these random variables x of n, n minus 1, dot maybe n minus I dot maybe n minus p. So, n minus 0, n minus 1, n minus I, n minus p. So, total p plus 1 actually is p plus 1 cross 1 is a random vector. So, corresponding correlation or autocorrelation matrix R x x will be, as we have seen already, and again after E I am not putting anything under subscript, it is up to you to understand. So, it is x n, that is this vector into its Hermitian. So, row column vector, then it becomes row after transposition and all elements conjugated. This is the meaning of Rxx. What is the shape of Rxx now? So, start with x of n, I am writing it here, x of n minus p, and then x of n star, x of n star n minus 1, maybe I write n minus 2 also, x of x star n minus 2 dot x star n minus p. Therefore, first see xn, this will be matrix. So, 1 comma 1 element will be xn into x star n, expected value of that. Xn into x star n is we have already seen these are variables. E of what is our notation? Ax n x star n minus k. This was R. I use the subscript xx for the time being to avoid clumsiness and all that. Let me drop that subscript. Just rxx k, rk. That xx I am dropping because otherwise this place will be filled with rxx and it will be a bit clumsy. So, just rk I am using as a notation rk. So, if k is 0, then xn into x star n a mod xn square r which is r0, and r0 will be the total power, okay, which is real, non-negative and usually positive. So, that will be xn into x star n, there is mod xn square e of that. So, this will be r of 0, then xn x star n minus 1 expected value, that is r 1, then xn x star n minus 2. Okay. So, that will be r 2 dot 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 dot. See, n is disappearing from here because of Whitehead stationary assumption, because it depends, correlation depends only on, correlation or autocorrelation depends only on the gap k. So, gap is 0, gap is 1, gap is 2, n minus 1, n minus 2 like that. So, lastly xn into x star n minus p, it will be r p. Now, x n minus 1 x star n, x n minus 1 x star n, what it will be? It will be, this is, if you call it mth index. So, this will be what? M plus 1. All right, if you call it mth, m plus 1 and then star. Okay. Let us see here x. We have already seen in the previous page the Hermitian property. Sorry, the Hermitian Rxs k and Rxx star minus k, they are same. We have seen so, x, now we have got this x n minus 1 x star n e of that, all right. So, if you call the index m, n is m plus 1. So, this is m plus 1, okay. M plus 1 meaning m minus 1. So, x of n x star m minus k, k is minus 1 here, all right, x of n x star m minus k and k is minus 1. So, this is your r x x minus 1. So, r x x minus k, if I make it, it becomes r x x star k. So, this is r x x star k 1. So, I am not using the x x subscript here for avoiding clumsiness, because too congested. So, x n minus 1 x star n, it will be nothing but or same thing. This has to be because after all this correlation matrix is Hermitian, we have seen. So, I comma j 1 comma 2 and 2 comma 1, those elements must be conjugate of each other, conjugate symmetry, and that is what is happening, r star 1. Then x minus 1 x n minus 1 x star n minus 1. So, index is n minus 1, if you call it m, x m x star m. So, mod of x m square expected value, which will be again r of 0, whether m here or n here does not matter, x m x star m k is 0, or that is x n minus 1 x star n minus 1 or x n x star n k is 0. So, it does not change because gap is 0. What matters is the gap. So, it will be r x x or it will be r 0, because n minus 1, n minus 1, no gap. So, gap is 0. So, there will be again R 0, same element. Then n minus 1 x star n minus 2. So, n minus 1, n minus 2. Now, gap is plus 1, all right. So, it will be R 1. Next element would be, if it is x star n minus 3, n minus 1, n minus 3, gap is 2. So, it will be R 2 dot 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 dot. So, n minus 1 and n minus p. So, gap is p minus 1, n minus 1 minus this index, n minus 1 minus this index, n minus p. So, if you subtract, it becomes p minus 1. So, R p minus 1. Then again x n minus 2 x star n. And by the same logic, here n minus 2. So, if it is n minus 2 and x star n, okay, if you call it m, it is m plus 2, which is m minus minus 2. Okay. So, it becomes R x x minus 2, but R x x minus 2 is R x star plus 2. If it is minus k, it becomes plus k. So, R x star plus 2. Second, from the Hermitian property also, if it is 1 comma 3th element, then 3 comma 1th element will be conjugate of that. Then n minus 2, n minus 1. In the same way, n minus 2, n minus 1. If you call n minus 2 as m, so n minus 1 will be m plus 1, and same thing will follow. So, it will be this R star 1. Then n minus 2, n minus 2, no gap. So, it will be again R 0. Then will be n minus 2, n minus 3. Now, it will be R 1 dot 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 dot. So, you can see one thing, along the diagonal same element is propagating. Then along this diagonal, subdiagonal, R star 1, R star 1, R star 1 is propagating. Similarly, along these R 1, R 1, R 1 is propagating. So, if you know one row, entire matrix can be constructed. Any matrix where of this form, that elements just go on, elements just repeat along a diagonal and again along each subdiagonal, that is called Toeplitz matrix. So, along the diagonal R 0 propagates, along next subdiagonal R 1 propagates, here R 2 propagates, like that. Here again R star 1, in a general Toeplitz matrix, it may not be R star 1, it may be any damn thing, like you can be A, B, C dot dot dot. So, A, B, 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 B. If it is C, 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 C. If it is D, 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 and like that. But here along with Toeplitz, this is Hermitian also. Say R 1, if it is R 1, it is conjugate only coming here and then propagating. So, it is an additional property on these. So, these are very important property of the correlation structure, correlation matrices of discrete time random sequences. Okay. So, we will continue from here in the next class. Thank you very much.